I will attempt to stand still, which is very hard when you have to talk with your hands and your feet. All right. Try to stand still. All right, so I think by now there's probably nobody in the room that hasn't heard the term digital twin. If you have not heard this term, I don't know where you've been for the last few years. It's a really exciting idea. I think, of course, as with any exciting idea, there's a lot of hype, but there's also really a lot of substance to the idea of a digital twin. And today I really want to talk a little bit about where I see the opportunities, but mostly about where I see some of the challenges. And those challenges really span across many people who are here and the expertise that's represented here at Multicore World. So right off the bat, one of the things about a digital twin is that there's no shared definition of what is a digital twin and certainly what is not a digital twin. And in my various travels, I hear many people say, oh, a digital twin is nothing but modeling and simulation. That's something we've been doing for many years. There's nothing new there. It's really just a new name and a lot of hype for something that we've done for a long time. I really believe that's not the case. I do think a digital twin builds on powerful modeling and simulation, but goes far beyond. While imperfect, I'm quite fond of the definition that's up here. This is a definition that came from a large community working group that came out of AIAA, that's the American Institute of Aeronautics and Astronautics, and that group published an institute position paper a few years back. The reason I like this definition is because to me this really speaks to the essence of a digital twin and how it is truly different from the powerful modeling and simulation that many communities have been doing for years. So a digital twin is a set of virtual information constructs that mimics the structure, context, and behavior of an individual or unique physical asset. So there's the first key difference. We're now not talking about modeling and simulation of a generic aircraft or a generic spacecraft or a generic building. We're talking about modeling of an individual. So we're talking about the personalization of computing. And as I go through, we'll think about the elements that makes that possible. Second, so continuing on here in the definition, is dynamically updated with data from its physical twin throughout its life cycle. So a digital twin is a living model. And again, we can think about the history of large-scale computing, and we can find examples where that is true. The weather forecasting community is one example where this notion of dynamic updating has been a part for many years. But in many other parts, and particularly in many aspects of engineering, that's not the case. Those high-fidelity simulations tend to be static. So that's really the key thing now, the key difference that the digital twin brings in, this notion of being dynamically updated, of having this interaction with the physical system so that the digital twin can follow the physical twin throughout its life cycle. And then the last part there of the definition, it informs decisions that realize value. And so often what we're doing with our large simulations is issuing predictions in order to support decisions. And you can think of whatever your favorite example is. The COVID modeling that we heard about earlier this morning is a great example of that. Again, there are examples where you can find the integration of decisions into the modeling and simulation world, but I think the digital twin really demands that integration and takes it to a new level. So lots of elements there. Really important to think about the core of the models and the simulations, to think about personalizing the way we compute to an individual asset or to an individual human being, thinking about the two-way flow of information between the physical and the virtual, the dynamic updating from data, and then the simulations driving decision-making. So this term has an interesting history. The term digital twin was coined in 2010. It came out of some work that was being done by NASA and the Air Force, so it has its roots as a term in aerospace engineering. This idea is much older, and as I've already alluded to, you can look across communities that have been historic users of computing and find examples that you might point to and say, hey, that really is a digital twin in operation well before 2010. One example that is sometimes pointed to is the Apollo program, and there's a really fantastic blog post from someone from Siemens that if you Google digital twin Apollo 13, you'll find this blog post where this blog post tells the story of the Apollo 13 mission, and we all know the story because we've seen the movie, right? I'm talking to an older audience today, so I know you guys have seen the movie, that the spacecraft, when it was up in space, there was an accident, there was an explosion, the spacecraft was damaged and was actually stranded up there in space, and it was sort of a big question about what to do and how to bring the spacecraft back safely to Earth. So where do the digital twins come in? The story goes that back in the Apollo program, and so now remember we're talking the 60s and the 70s, when NASA launched a physical spacecraft into space. At the same time, they kept a digital simulator on the ground in Houston, and so that wasn't called a digital twin, but this now really was the digital twin that was following along as the physical spacecraft was going on its mission. And when the Apollo 13 crisis happened, again, the story goes that NASA were able to take the data from the physical twin, stuck up in space, feed that data into the digital simulator on the ground in Houston, dynamically update the conditions of the simulator, and then use it to do all the what-if scenarios and drive the decision-making that ultimately brought the astronauts back home safely. So when was that? 1970, 1971? So 50 years ago, there really was a digital twin in action. And one of the reasons I like to talk about this example is that it's a very good reminder to us that in order to be useful and to drive value in our decisions, the digital twin does not, and I firmly believe does not have to be an exquisite replica of a physical system down to the very finest level of detail. Think about the models. Think about the computing power, think about the sensors and the data that they had back then, 50 years ago. And of course, they were nothing close to what we have today, but nonetheless, this integration across the data models and decisions was able to really drive value. So 50 years on, we now have a really great term to describe this idea. And one of the reasons I really do like this digital twin term is because it's something that people on the street can understand. And I don't know how many of you in the room have struggled over your career to explain to your brother or your sister or your mother or your neighbor what it is that you do. But as a computational scientist, it's always been very hard to talk about, explain what I do. Now I can tell, my kids say, my mummy builds digital twins of aircraft, and people get it. And we can laugh about it, but convincing decision makers who are not trained as computer scientists or engineers or mathematicians of the value of computing and the way it can change the world is so incredibly important now more than ever. And this notion of a digital twin, I think, is a very powerful one that non-experts can grasp onto and think about, again, this potential to revolutionize decision making. Some of the pictures up here, these are some of the things we have going on at the Odin Institute that relate to digital twins. So I have been working, and I'll talk a little bit about this as I get going, on digital twins, thinking about self-aware aerospace vehicles. Primarily I work on aircraft, but we've recently started a newer project with the Space Force, thinking about digital twins for space infrastructure. And again, if you want to think about societal grand challenges, the congestion and just the amount of stuff that's up in space, not knowing what's where, what condition it's in, this is a looming crisis for humanity. And so again, thinking about this notion of a digital twin, the virtual models, the data we can collect, the two-way integration, and then the driving of decision making, digital twins is a high priority for the Space Force, and I think it's a really important area to think about. Here on the left, this is a picture of some work from my colleague Omar Gattas. So this is a high-resolution model of Antarctica, and again, thinking about digital twins and how they can drive understanding of what's going on in the natural world and drive our decision-making, not just around, say, policy for climate change, but decision-making around multi-million, if not billion-dollar decisions about where to deploy sensing infrastructure, where to drill the next ice core in Antarctica, how to build these extremely complex and expensive ocean observing platforms, and where to deploy those sensors, given that we can't possibly sense everywhere on planet Earth. So another really important and I think very active area in terms of climate. And then all the way over there on the right, we have quite a bit of work in the Institute going on in digital twins and medical applications, and I'll talk a little bit about some of the work we're doing on oncology later on. But again, this notion of advanced computing or a sophisticated model combined with data to personalize decisions. This is patient-specific medicine, right? So this is, again, a grand vision, a grand challenge, a really exciting area for digital twins. So it's wonderful. You know, we could all probably go around the room and each one of us could talk about our favorite system, whether it's an engineering system, part of the natural world, or maybe a biological system, and we could think of the ways in which digital twins could be a game changer. Of course, it's a hard problem. It's a really, really hard problem, and I know I'm being videoed, but maybe I'll say, despite what some companies say that you can buy by clicking on their website, I do not believe that digital twins for these kinds of complex systems are even close to being a reality at the scale needed today. There are real challenges, and those challenges really relate to this challenge of predictive modeling, because in all those examples I've given you, the value of the digital twin really comes in being able to take a model, combine it with data, and then issue predictions about situations that haven't happened yet, or issue predictions about the what if. What if this patient were given this treatment or this treatment? So we're really talking about a need to be predictive. Why is this such a grand challenge? So first of all, again, think of all the examples I've given, whether it's in climate, in aerospace engineering, or in medicine. We're talking about complex physical phenomena. These are multi-scale, multi-physics phenomena. And despite the incredible computing power that we have and the incredible algorithms that we have, it's still not routine to do high-fidelity simulations at the scale we're talking, at the scale of an entire human patient, or at the scale of the full Earth. And I know we have many colleagues here from the US Department of Energy National Labs. They will tell you that some of their most sophisticated calculations run for months and even years on those incredible supercomputers that we just heard about earlier today. So it is still a huge challenge to just simulate these complex systems at the scale needed to be predictive. Second, the challenge of cyber-physical interactions. The moment we're talking about a digital twin and that two-way integration of the models of the virtual and the physical, we're talking software, hardware, sensors, automation, and all the challenges that come with that, not least of which are the issues around privacy and security. And I often sort of think of the day when I will have a digital twin of my car or a digital twin of my aircraft, and just like I have to be concerned about security for the physical asset, security for the digital twin is going to be a huge issue and really a difficult one to deal with. So again, that second bullet, just tremendous challenges. Third, these are systems, whether we're in the engineered world, in the natural world, or thinking about ourselves as human beings. These systems, I'm going to refer to them all as systems, so when I say system, think about yourself as well. We have a complex life cycle. If you're an aircraft, you have design, conceptual design, detailed design, manufacturing and operation, and then your post-life. For a human being, just think of all the phases of your life cycle. And what's more, the data that is collected over that life cycle is not in any one place. There are so many different stakeholders. Even the question of, we as human beings, do we, actually Nicholas, you led off this morning, you said you own your own image. Even that itself is a complex statement. But this complex life cycle, again, this is where the value of the digital twin really can come in, because the fact that this life cycle is so varied and changing, and that we can collect data over the life cycle, that's the opportunity, but it is also posing an incredible challenge. Fourth one there, limited data. Yes, we live in the era of big data, but again, I want you to think about some of the key examples that I've given. Aircraft, I'll talk a little about aircraft structural health monitoring, the climate, the Earth, digital twin of planet Earth, and then a medical example. Think of maybe a cancer patient. The data may be big, but the data are incredibly sparse. The observations are noisy and they're indirect. By indirect, what do I mean? In order to ascertain the health of the aircraft wing, we can take measurements from the outside looking in. We have sensors, strain sensors on the surface of the wing, and we need to infer what's going on the inside. The same is true for us as a patient. We can take MRI data, we can take observations from the outside, trying to infer what might be going on, infer what the properties may be of a tumor inside one of our organs. So those measurements are noisy and indirect, and they're expensive and intrusive to acquire. It's really not just a matter of waiting until there's more and more and more data, because I have to say, it's just not going to happen. Every sensor on board an aircraft consumes weight, adds weight, consumes power, so it has to buy its way onto the aircraft. Every piece of data collected of a human patient is costly and intrusive, requires a sick person to go and to be tested. And on planet Earth, again, can you imagine a future where we have sensors deployed? We look out into Wellington's harbour and see just sensors everywhere. So we are we really are going to be in the range of limited data. And by the way, making good decisions is about predicting the future. And so when I read about AI models that are going to learn to predict the climate, I'm wondering what data are they going to be trained on for that future that hasn't happened yet. This is a really, really important challenge that has to come into play when we think about digital twins. And then lastly, evolving asset state. As if things weren't difficult enough, these complex systems are not going to just sort of stay as they are. They are going to evolve, they're going to degrade, they're going to be damaged, they're going to undergo maintenance and maybe upgrades. And if we're going to make good decisions that people's lives depend on, we're going to need to track all those and reflect them in the digital twins. So this might sound a little bit gloomy, but I think this is great, because as an academic, I love that there are these incredible challenges out there that really need the community to come together. And Nicholas, you made this comment in your opening remarks about community coming together around this truly is a grand challenge that will help bring computing to address some of society's biggest challenges. And now I'm just realizing I have no idea what time. I should also have said at the beginning, it is right about my bedtime now, and so I do appreciate Nicholas. I should have requested an early morning, but I did wake up super early, and I managed to run up Mount Victoria before the storm came in. So, all right. You may have already sort of gotten a gist of one of I guess my soapboxes, which is I really get concerned that so much of the narrative in our field at the moment is around data, is around machine learning and AI and the opportunities that come along. That's a huge opportunity and absolutely is an area that needs to be pushed forward. But again, I want to just repeat something I already said. We have to remind ourselves for some of these most complex systems, these most complex problems where, not to be too melodramatic, the future of humanity depends upon big data alone is not enough, and I believe will never be enough, certainly not while I'm still alive. And so what does that mean? That means as we think about digital twins, it can't just be about the data and the machine learning and the AI. Those are part of the story, but we really have to think about digital twins that incorporate predictive power, interpretability, and domain knowledge that come with physics-based models. And this, by the way, has real implications for the future of computing, especially as we think about what might come beyond the exascale machines and the kinds of architectures and whether they're well suited to the simulations that represent those physics-based models. And that's a topic we could really talk about for quite some time. So digital twins, I really see it as a scientific grand challenge. It's a scientific grand challenge that I see as, first of all, really needing fundamental advances in enabling technologies. Again, I hear sometimes from folks, especially folks out in industry. They say, oh, digital twins is not a technical challenge. We know how to do it from a technical standpoint. It's really an organizational challenge. I agree that it's a big organizational challenge, but I completely disagree that it's not a technical challenge. There are so many technical challenges that are needed, fundamental advances that are needed in the enabling technologies. And I have some of the enabling technologies up there on the slide at the top there. So again, those predictive physics-based models and simulations. Don't even begin to think that we can simulate complex systems at the scale needed today. We do a lot of work with the Air Force on simulating rocket engines. One single simulation for the rocket engines takes about 3 months, and we're not even there resolving the scales we really need. So as we're doing, we're coming up with surrogates and machine learning with the Air Force, they're running these simulations and they're sending us kind of new data every week. It's painfully slow. So again, really fundamental advances needed to go to the scale that digital twins demand. Uncertainty quantification, you're going to hear me touch on this one quite a few times. If we're going to have digital twins informing decisions where people's lives are at stake, we have to understand how good those predictions and those decisions ultimately are. So uncertainty quantification and doing it at the scale needed is a huge challenge. Optimization and control, these sort of sit at the heart of decision making. Again, mature technologies in some sense, but taking it to this digital twin level, again, needs fundamental advances. High performance computing and edge computing, one of the things I really like about a digital twin is that it's going to need both. And even thinking about how the different kinds of computing we have are going to interplay and how a digital twin will be distributed across computing resources, I think is a fascinating problem where we don't yet have all the answers from a very foundational approach. Inverse problems and data assimilation, it's easy to say, take a big giant model and assimilate data and update it. It is, again, a technology, something that we can do at some scale, but to do at the scale needed where these models, think of this model of planet Earth that the destination Earth people are building. Think about how many parameters that's going to have, and think about doing that data assimilation problem and quantifying uncertainty. That is truly a grand challenge. And then AI and machine learning, I have there scientific machine learning sort of to emphasize that we are likely to be in this sparse data or this data poor regime. Again, tremendous challenges in terms of the explainability of the methods and having the different approaches work when you don't have reams and reams of data, and it's understanding extrapolatory properties and how well can we trust these kinds of methods, the machine learning models and the decision making when we go beyond, and many, many more. Okay, so fundamental advances in enabling technologies. Second, unprecedented integration across domains. Digital twin, I think, is exciting because of the number of different maybe traditional areas it brings together, and then partnerships across sectors. And again, I could probably talk for 15 minutes on each of these. I think they're clear. This is just, again, a huge challenge, but a huge opportunity. All right, so I wanted to just really quickly, Nicholas said I wasn't allowed to give a deeply technical talk, and so I won't. But I wanted to give you a few just sort of brief highlights of some of our recent and ongoing work in predictive digital twins, because I think you'll see through the technical work some of the way that the themes, the sort of high-level vision that I have just articulated come through in what we've done. So the first one is around reduced order modeling. So reduced order models, surrogate models, approximations, basically approximations of sophisticated high-fidelity simulations, I think are a key enabling technology for digital twins. This has been one line of work that we've had quite a bit going on in the last years. The pictures that you see here are this one here in the top left is an unmanned aerial vehicle, a little UAV that I have in my research group. It actually currently resides in my garage. I said it, my garage. my garage in Austin, Texas. It had to come home out of the lab, and it's just sort of stayed in my garage, and now it's become like a family experimentation. But we have this vehicle that we designed and built together with Aurora Flight Sciences that is instrumented, that we do some of our work on. Then in the other pictures, you can see the digital twin that we build of that aircraft, and again, this is a relatively simple problem, building structural models, and we're really going after the digital twin of the structural health of the aircraft. So it's a system for which we have great predictive physics-based models. We have finite element simulations that run pretty quickly. Even so, the kinds of things we need to do with the digital twin, like real-time updating of the models while the vehicle is flying and potentially gets damaged, and then using those updated models to drive decision making, even the 1 to 2 minutes of a finite element simulation is just way, way, way too long. So that's where things like reduced order models come into play. How do you come up with approximations of these sophisticated models that you trust, approximations that you can run really quickly, maybe on an edge device and in real time, and do so with a level of trust. And again, this is an entire talk in itself, but this is one area where I think machine learning also has a large role to play in terms of thinking about powerful surrogates that are lightweight, can be deployed on lightweight devices, and drive that dynamic updating and decision making. The second thing that we've been focusing on is we really have been asking this question, and again, I'll come back to this when I start to talk about the path forward, but asking this question of how do you get away from every time you go to create a digital twin, it's like you start with a clean sheet of paper and you architect a digital twin for your particular system, and then when you're done, and then the next time you need to do it, you start again. How do you get away from that and get more to a common language or a common way of thinking about digital twins that transcends different domains and transcends problems? And to move forward on this challenge, we really took a good look at the field of robotics. So I think in robotics, you could say this is a field where for a long time there has been this notion of the physical and the virtual and the two-way interaction between the two. And within the field of robotics, the notion of a probabilistic graphical model, thinking about this complex system, this digital twin and its physical twin as a graphical model. And so as part of that, one of the things that we first have to do is we need to have a language for how do we think about the digital twin. And what you see here on the slide is the way we have 6 different elements, the way that we characterize a digital twin. What is the physical state? What are the things about the system that I want to be able to represent and track? What's the digital state? Recognizing that the physical state is probably an infinite dimensional quantity or sets of infinite dimensional quantities, pressure fields, temperature fields, structural health. I'm going to have to represent that digitally in some way that is tractable. Thinking about the decision space, what are the control inputs that I can take? Thinking about the observation space, what are the data that I have? Quantities of interest, what is it that I need to be able to predict in order to make decisions? And then rewards, how will I judge whether a reward is good? So laying all that out formally, and then from a mathematical standpoint, really formally thinking about the digital twin as a graph, and particularly as a probabilistic graphical model. And so now let me come back to another really important point, which is I absolutely believe that digital twins have to have uncertainty quantification baked in from the beginning. I think you could go off and spend 3 years building an exquisite digital twin of a system for somebody, and then if you give it to them and this digital twin comes back and says, the answer is 6, or Nicholas, the answer is yes, launch that spacecraft or take that maneuver, and you say, but how much confidence do you have? And then I'll go back and probably have to spend another 20 years figuring out how to do the uncertainty quantification. We have to get the uncertainty quantification, the validation, the verification baked into the digital twin from the beginning. And this is one thing that the probabilistic graphical models can do for us. So as we now start to think about in the physical space, those physical states, those are the S's, the observations, the O's, and the actions we can take in a probabilistic graphical model, these are all represented as random variables. So we're thinking not just about these quantities, but also distributions that represent our belief in what we do and don't know about those quantities at any point in time. And then we can really start to map out the entire graph that again represents the digital twin and the corresponding physical asset. So what we're looking at here is a graph with time going from left to right, and don't get too caught up on what arrow is connected to what nodes, but maybe you can see that the graph is telling me what is it that I can observe of the physical state, and as I come down now to estimate the digital state from those observations, what I have now is a graphical representation of an inverse problem or of a data assimilation problem. And then as I start to predict quantities of interest and characterize rewards that then drives decision making, what you're looking at in the graph there is an optimal control problem that you could solve with dynamic programming or reinforcement learning or whatever your favorite decision making is. But really, again, mathematically representing the digital twin as this graph, which means that our digital twin mathematically is a giant joint probability distribution that encodes the relationships between all the different pieces of the system, encodes the relationships between the digital twin states, the quantities of interest, the rewards, the future actions, all conditioned on what we have observed and actions that we've taken in the past. So this is a sort of, I think, a really powerful way to think about a digital twin, because when you think about a digital twin in this way, then all the different use cases, whether you're thinking about virtual inspections or forecasting or predictive maintenance or some kind of an optimal control of operations or some kind of a learning across assets, all these different tasks that you want to do to the digital twin or with the digital twin all just light up different parts of the graph. And I've written them there as, sorry, Nicholas, I couldn't avoid the equations. I've written them there as conditional probability distributions, but just think of them as lighting up different parts of the graph depending on what it is you're trying to do. And again, importantly, uncertainty is baked into all of this so that every time we are solving an optimal control problem to issue a decision, we are doing it with uncertainty quantified, and you're telling me what is the risk level or how much confidence do you need to have in a given decision. So quite a bit of work we've been doing in this. Again, I want to point out it's all very nice to formulate these things in this way. Being able to work with a probabilistic graphical model at the scale needed to truly have a digital twin of a truly complex system where these states and quantities of interest may have thousands, millions of degrees of freedom, that is still a grand challenge from a very foundational algorithmic and computing. And no matter how much that top 500 line keeps going up and up and up, we're a long, long way from being able to compute these kinds of things at scale. Let's see. So we've sort of applied that, sort of put all those pieces together, the reduced order models that are enablers, the probabilistic graphical modeling. We've done a lot of studies with the aircraft that you saw on one of the earlier slides, again, where the setup is this idea of an aircraft flying around. You can imagine one day it's going to be the Amazon drones delivering packages or delivering pizzas for Super Bowl parties or whatever they're delivering, but flying around, getting damaged. It's all going to need to happen autonomously, right? Sensors on board the vehicle sense that something's happened, the models are dynamically updated, the decision-making loop is run, and the vehicle needs to decide what to do so that it can either complete the mission or land safely. So this is a little bit older work. This work was published. You can see there the reference there from 2021. One of the really exciting things that has happened, and this is one of the really exciting things about being in the Odin Institute at the University of Texas at Austin, is that we did this work on digital twins applied to the aircraft, and then one day I started talking with my colleague Tom Yankelov, who directs the Center for Computational Oncology, also in the Odin Institute. And this notion of coming up with a digital twin for a cancer patient was something that's of tremendous interest in the oncology field. And so then as we start to talk, and you remember, go back to what I said a few minutes ago, which is how do we get away from having to start with a clean sheet of paper every time? That was really our motivation in articulating this probabilistic graphical model. So now we can take those same 6 elements and ask the question, if it wasn't structural health of an aircraft wing you were worried about, but rather the health and decision-making around a cancer patient, what would those 6 quantities look like? And you can see that the mathematical model sort of maps really well. The state now is thinking about tracking the properties of the tumor. The observations are different. They're all the observations that can be made in the medical setting. The control inputs are different, but it's the same kind of notion. We can either make a decision that's around a treatment, an action, or we can make a decision to acquire new data, the quantities of interest and the rewards. So just like we did for the aircraft, we built a probabilistic graphical model representation of a digital twin for a cancer patient, and we've been working with the collaborators in the computational oncology to apply this. And the example you see here, this is a glioma, so this is a brain tumor, where one of the things I love about it is the steps are so similar to what we do in the engineering setting, where we're taking data, we're calibrating this digital twin to the individual patient, and then using the calibrated digital twin to dynamically track what's going on and then to do optimal decision making. So this is work in progress, but it's been really, really fascinating, and again, that's something we could get to maybe in the questions. I don't know if there's folks here from the medical background, but the revolution that is going on in medicine right now with computing, with digital twins being just one example, it's just incredible, and it's something that I think we're going to see a huge amount of in the coming years. All right, let me skip right over this one. So so that's just a little bit of a. Actually, I skipped over this one, but let me just spend 10 seconds and say Omar Gattas and I recently were awarded these MIMIC centers. So this is a multifaceted integrated capability center to advance the multifaceted mathematics for predictive digital twins. And Omar came up with the logo that you can see there, integrated multifaceted mathematics of digital twins, integral of m squared dt. He's very proud of that logo. It's almost been obscured there. But this is really exciting because we really have a chance to push forward on some of these foundational issues I've talked about in collaboration with Brookhaven, Argonne, and Sandia National Labs, with the 2 driving applications you see here, coupled ice sheet ocean dynamics for climate. And then this is one I haven't talked much about, but digital twins for manufacturing of, well, for advanced manufacturing in general, but particularly for advanced manufacturing of semiconductors. Again, there's huge opportunity there to really think about advancing the state of what's possible. And so this application is in collaboration with Brookhaven. So this is just launching. It's a 5-year center, and I'm really excited about what we could do there. Okay, so looking forward, so where are we? So I said, you could go back to Apollo 13. You could think about these very, very early deployments of digital twins that weren't called digital twins. You could fast forward to 2010 when NASA and the Air Force gave us this great term to think about what it is that we're doing or why we're doing all these simulations. What are you going to pick up? What number is it? I managed to leave my glasses in Texas, so actually that's big enough. I can read that. I'm probably going to be less than that. So 2010, we get the term. In the, 12, 13 years since then, we're really starting to see some exciting applications of what digital twins can do. So the US Air Force has been using digital twins for sustainment of military aircraft, and we're starting to see all kinds of other applications pop up in medicine and civil infrastructure. So where are we? Where kind of are we in this journey of digital twins, and what's next? So I've already mentioned this point, but I think this is a really important one. I think we're in the custom phase of digital twins, where digital twins are still very much something that can really only be done by the expert on this one-off basis. And I think we as a community really have to ask this question: how do we move from the one-off, expert-driven digital twin to accessible, robust digital twin implementations at scale? And unless we can answer that question, we're not going to achieve any of this grand vision that I laid out in the very first part of the talk. I co-authored an opinion piece in Nature Computational Science together with one of my colleagues at Odin, Michael Sachs, and some colleagues from Turing Institute, Mark Girolami and Stephen Niederer. We really sort of focused in on this question of how do we scale. So before we think about the future, I think it's always really valuable to think about the past. And for me, the finite element method is a great sort of case study of this journey from the expert-driven to the impact at scale. And I know there's a lot of computer scientists here, but put up your hand if you're not familiar with the finite element method. Okay, so if you're not. Okay, so the finite element method literally has built the world around us. The chair you are sitting on, the table your stuff is on, the building we're in, there will be structural analysis that has gone on for all of these things, and the chances are it was done with the finite element method. It is just an absolute incredible impact of mathematics and computing on applications. So if you trace back the history of the finite element method, the origins, the mathematical origins, and even then the early computing, which by the way, a lot of which was done again in aerospace engineering, we're really going back about 70 years. And if you look at the finite element method today, it's the workhorse of, I said engineering analysis and design, I probably should have said structural analysis and design, but also used in many other physics, and is in the hands of every engineer. Pick your favorite software that's got finite element running in behind, and by the way, many non-engineers, a lot of folks who work in architecture or other sort of non-engineering design. And you could ask the question, what has it taken to go, if we go back to the early days in Boeing, and actually you don't even have to go, well, maybe it is that far back, but I remember back in the last century when I was a graduate student, the very first thing that you did when you started graduate school is you had to write your own CFD solver, right? And in Fortran, yes, and actually, or in C++ maybe. But every student coming in would write their own finite element solver or write their own finite volume CFD solver. That's not the case anymore because there's incredible, powerful software, some of which, by the way, is open source that you can reach to. So what is it that's changed? So the first one really cannot be underestimated, but I think it's often neglected, which is the mathematical maturity of the underlying methods enable robust use by non-experts. So what does that mean? That means things like mathematicians proving theorems about the convergence of these methods under idealized cases. If we don't have that very foundational mathematical work, these methods are built on houses of cards, and when you put them in the hands of the non-experts, don't ask me to fly on that aircraft or walk in that building. So the mathematical maturity, and by the way, I'm going to be talking about digital twins, but I think everything I'm going to say on this slide also applies to machine learning in spades. So the mathematical maturity is incredibly important and has to be invested in. Second is the computing advances, both in the hardware and also in the algorithms, has gotten to the point, and again, to go back into the old days when I was a graduate student, you used to set your CFD code that you wrote yourself in Fortran running, and then you would go home and you would hope that nothing happened, and you would come in the next day and check on it. Now, we have so much power right, on our desktops or on our high-performance clusters, even though those multi-scale problems remain out of reach. It's now at the point that everyday engineers have enough computing to actually be able to apply things to realistic problems on human timescales. And then a third really important part are flexible software implementations that make these methods accessible and broadly applicable. And by the way, some of those software implementations are wrapped up in commercial packages that you have to buy, but others are in open source implementations that are incredibly powerful and get a community behind them. So again, I'm talking about the finite element method. I think there's some sort of real lessons and lessons to be learned in terms of what it takes of what it has taken and where we need to go. So back to digital twin, the world needs accessible, robust digital twin implementations at scale and across domains. We need all of those things on the last slide. We also really need to think about the computing and the data infrastructure. The digital twin brings in the data piece, and I'm sure that this week we're going to have maybe a lot of discussions about data and data that's sort of distributed and what that means for the future of computing and the future of our infrastructure. The software play an incredible role. Actually, the standards I didn't mention on the last slide, that may also be a factor in what's going on with the finite element method. And then the partnerships, just so incredibly important. Okay, this is my last slide. I thought I would just close by emphasizing, I'm an academic. I cannot help but make sure that you leave with the message that digital twins are not a done technical solution. There are real needs. Some of those needs are around partnerships that will be done with industry, but there are real research needs for digital twins. I talked extensively about predictive modeling. Let's not let the world think that we are done with forward simulation, because we are not. Validation, verification, uncertainty quantification, so important, have to be baked in from the beginning. And I'm actually fairly concerned about some of the large-scale efforts not having uncertainty quantification baked in from the beginning. By the way, that makes the problem, I don't know, 1,000x more difficult, 1,000,000x more difficult, but we have to do it. Data models and decisions across multiple scales, the data assimilation, the planning and control, scalable algorithms for updating prediction and control, probably in real time on deployed platforms, and then digital twins at the system and system of systems levels. And Nicholas, you mentioned this earlier today. So many challenges in how we get to that system of systems levels, things like decoupling, decomposition and coupling of subcomponents, multi-fidelity methods, and so on. All right, I know I was not nearly as humorous as the last speaker, but hopefully I've at least given you a couple of things that you either agree with or would like to disagree with, and we can have some great discussion afterwards. But thank you very much. Don't go anywhere.
So we are